Welcome back, everyone. I'm Professor Rhett Smith for ProtonGuru.com, and today we're covering lessons 7.3 and 7.4, where we'll talk about infrared spectroscopy. In lessons 7.1 and 7.2, if you've covered those lessons already, you've seen that molecules can absorb energy in the ultraviolet and visible regions of the spectrum. Here we're talking about what happens when molecules absorb energy in the infrared region of the spectrum. Infrared light has a lower energy than visible light, and what this leads to is the molecules undergoing stretches and bends to the bonds in those molecules. These bond stretches and bond angle bends are collectively known as vibrations, and infrared spectroscopy is a type of vibrational spectroscopy. Now, the way that energy is typically expressed on the x-axis in an infrared spectrum is somewhat unique and unusual compared to other ways you may have seen energy expressed. You've probably learned along your courses that energy is equal to the frequency times Planck's constant, which can be converted to hc, so Planck's constant speed of light, over the wavelength of light. So if you take this constant out, energy is proportional to some constant times 1 over the wavelength. And if you express that wavelength in centimeters, we have what is known as the wave number, given this symbol with a little wavy line over the top of the new symbol. So the units you'll see on the x-axis for an infrared spectrum will be given in reciprocal centimeters or wave numbers. And that may be an unusual way to express energy, but the important thing here is to understand that the larger wave numbers correspond to higher energies because the wave number is the reciprocal of the wavelength. Now, I mentioned that when infrared light hits a molecule, it causes bonds to stretch or bond angles to bend. Now, bonds can vibrate in these ways in different manners, and each of these vibrational modes requires a different energy. So you can have the same unit within a molecule absorbing different energies of infrared light. And I'll illustrate this just by looking at a simple CH2 unit in some hypothetical organic molecule. Let's say you have these two CH bonds stretching, and they stretch outward at the same time, or pull inward at the same time, so that they're always stretching or compressing in a symmetric fashion. This is called a symmetric stretch. And notice that you're pulling nuclei and moving electrons around when you stretch a bond. Because the bond has 2 electrons here, and if the bond becomes longer, the nucleus comes out here, then that bond is going to have to stretch, meaning the electrons have to cover a larger area. That's going to take a different amount of energy than if this H is compressing while this CH bond is stretching. So this is known as an asymmetric stretch. We can talk about an out-of-plane bending mode. So if we consider the plane made by these 3 atoms, and you start to pull both these H's towards us at the same time to bend those bonds from their initial geometry, then those 2 H's are both moving towards us or away from us at the same time. That would be known as a symmetric bending mode. If, on the other hand, that set of CH bonds is distorting the HCH bond angle by having one of the H's move towards us and one away, so they're not moving both in the same direction, this is an asymmetric out-of-plane bending mode. Now, in those cases, the H's were coming out of the plane in which they initially sat. What if we have an in-plane movement of those H's where the bond is still bending? For example, if these H's both move out at the same time, and then they can come back in at the same time like a pair of scissors opening and closing, this is known as a scissor mode or a symmetric in-plane bending mode. On the other hand, instead of the H's both moving away so the molecule will maintain the symmetry around this midpoint, what if, looking at that midpoint line, one of the H's moves closer to it and one of them moves further away? Well, they're moving asymmetric with respect to the plane of symmetry there. So this is an asymmetric in-plane bending mode. Or what you can envision is these H's both move that way, and then both move that way, and then both move that way. They're kind of wagging back and forth like a tail on an animal. And this is referred to as a wagging mode or an asymmetric in-plane bending mode. So even for a simple CH2 unit within a molecule, I'm showing you 6 different ways that you can engage in a vibration that could be excited by absorption of infrared light. Each of these would take a different amount of energy. So the point here isn't to memorize these 6 different things necessarily, but just to recognize that even a simple unit within a molecule can absorb infrared light at several different energies. And there's a little more detail about what's going on in the course of a molecule absorbing light in the infrared region in the reading. But now let's look at material in lesson 7.4 on what actual infrared spectra look like. Well, we talked about the wave number axis, the energy axis. We have high energy, around 4,000 over here, and low energy, somewhere around 500. This is usually the span of energies covered by a typical infrared spectrum for an organic molecule. Then you have percent transmittance. That means what percent of the infrared light that shines into the sample comes out to be detected at the other side. If nothing is blocking the beam of infrared light, if nothing's absorbing the infrared light, of course you'd have a line where all the infrared light at every energy is passing straight through to the detector. 100% is transmitted through the sample. If none of the light, the infrared light, is making it to the detector, you'd have 0% transmittance through the sample. So what you see is when a molecule has bonds that absorb infrared light at a certain energy, like you see this spike coming down, each of the downward pointing tips is where you have an absorption of energy. So, for example, let's look at peak A in the spectrum. You see that peak A absorbs infrared light at somewhere around 3,000 reciprocal centimeters. And the transmittance, the percent transmittance, is around, let's say, 25%, which means that those bonds are absorbing 75% of the infrared light energy at that energy. Peak B absorbs around 1750, and it absorbs pretty much all the light with almost none transmitted through the sample. So that's what we're seeing in a typical spectrum, but how does that allow us to learn information about the sample giving that spectrum? Well, it turns out that each type of bond has a characteristic energy of absorption for infrared radiation. And as you might expect, some of the stronger bonds, like a triple bond in a CN or CC triple bond, would be harder to stretch, require higher energy than, say, a CC or CN double bond. And then you have specific absorptions for aromatics, for CC double bonds, CO bonds, OH bonds, and some of these are going to be easier to pick out from an infrared spectrum than others. One thing I do want to note is that more polar bonds tend to absorb more strongly. And you see this little column on intensity. You see the polar carbon-nitrogen bond has a similar energy of absorption compared to the CC triple bond. Right, so if we look back at the spectrum, they both absorb around here. So CC triple bond or CN triple bond. The difference, though, is that because the CN bond is much more polar than the CC bond, you see that you have the intensity of the band, how much light it absorbs, being medium to strong. M is medium, S is strong. But the CC triple bond is weak to, at best, medium absorption. And you'll see similar trends for a CO double bond that's very strong all the time, compared to, say, a CC double bond, which is just medium, or an OH bond, which is very strong. BR means broad, meaning that its shape would be like that, instead of sharp, like the other peaks that aren't indicated as being broad. So CH medium, sharp, OH broad and strong. So the polarity has something to do with the intensity of the peaks as well. So a couple take-home lessons. Stronger bonds are harder to stretch. For example, it takes more energy to stretch a CC triple bond as compared to a CC double bond, or an OH bond versus a CH bond. Secondly, the more polar bonds will absorb more light. So if I have a compound containing both a CO double bond and a CC double bond in the same compound, the CO double bond is more polar. You'll see it absorbs more of the infrared light than the CC double bond within the same compound. So knowing that stronger bonds require more energy to stretch them, we do need to pay attention to things like resonance influences, because resonance influences the bond order and therefore the bond strengths. Consider an amide, for example. This is a very good example of two resonance contributors to the structure, so that if we go ahead and draw a resonance hybrid structure for the amide, we would have to have some double bond character between the O and the carbon and the nitrogen. And we'd have some negative character there and some positive character there. Now you'll see that the resonance hybrid, which is a better approximation of the real structure than either resonance contributor itself, we see the CO bond is not a full double bond. It's weaker than in, for example, a ketone that does not have resonance stabilization. And for that reason, we would expect the amide CO stretch to have a lower energy of stretch than the CO bond that is a full double bond in the ketone. Now, if you take all this information together, there are a variety of different ways you can use this information to try to identify particular functional groups in a given infrared spectrum. And here's something of an infrared spectroscopy decision tree. And you can really start jumping into this decision tree at any point and looking at the different spectral features that correspond to different functional groups. And as you go through this decision tree, what you'll discover is that all these peaks we're looking at are primarily, not entirely, but primarily on the left-hand side of the spectrum if we go back and look at the scale. And we discover that most of the peaks we look at are kind of in this left-hand side of the spectrum. This is the area that we call the functional group region. And by looking at peaks in this area of the spectrum, we can generally pick out specific functional groups that are in a molecule. This is the true strength of infrared spectroscopy. The other region over here is generally less useful due to overlap of many different peaks. This area is called the fingerprint region. So let's take a look at the functional group region. Recall that we have these different peak absorption energies, and think about how we can use this decision tree or information contained in this tree to figure out what functional groups might be present in a molecule. Now, one of the particular functional groups that's especially easy to pick out is the aromatic group. Here's benzene as a simple example. Now, if there's an aromatic ring, you have to have several features. One mistake that students starting out to look at infrared spectra make is they'll see one of the features and say, oh, it must be aromatic. That would be a mistake. This functional group has to feature the CH bonds, if in fact there are any H's attached to the aromatic group, a CC double bond, and of course these CC double bonds will be a little weaker than isolated alkenes because you can draw a resonance to delocalize those bonds around the ring in an aromatic system. And you'll have to see overtones that usually appear between 1680 and 2000 reciprocal centimeters. And I'll show you what those different features look like in a bunch of example spectra that we'll look at in the next few slides. One of the most prominent features in infrared spectra where these groups are present is the CO double bond stretch. This stretch occurs between 1650 and 1850, generally right around 1700 in an infrared spectrum. If you see that in the spectrum, it's important to consider whether you might have an aldehyde, ketone, carboxylic acid, amide, anhydride, or acid chloride. And if you have any of these groups, OH or NH groups, you can look at the far left-hand side of the spectrum. A strong band, generally, these bands have different shapes depending on whether there's an OH, NH, or NH2 unit. If there's a U shape, you have an OH group. More of a V shape is generally an NH group, and this distinctive W shape, which is two V's, corresponds to two NH stretches instead of one that gives you a V, that is an NH2 group. Now, the reason for this broadening of the peaks, these are all kind of broad compared to the sharp peak you expect for, say, a CO double bond, comes from the fact that you have hydrogen bonding. We talk about this in the primer, and you can do your reading there. But if we have both a CO double bond and one of these groups, it stands to reason that you'd have something like a carboxylic acid, CO double bond and an OH, or an amide, or an amide with two H's on the nitrogen. Now, it's also possible if you have this broad peak for an OH and a C double bond O that you have both a ketone and an alcohol. We'll see a couple examples of molecules having two functional groups. Of course, there are other carbonyl CO double bond containing functional groups that do not have an OH or NH unit in them. For example, we could consider aldehydes, ketones, anhydrides, or acid chloride still. Now, if we look at the acid chloride, it often has a cleft shape to its CO double bond. It also has a CCl stretch around 600 to 800. This is usually a little harder to see. But you have kind of a strange looking shape to the CO double bond. This is often but not always the case. If you have an aldehyde, one unique feature that the aldehyde has that no other molecules we'll talk about have is the CH stretch for the H that's attached directly to the carbonyl carbon, the same carbon that has the CO double bond. if you have a feature, just two peaks, one at 2720-ish and one at 2820-ish, those correspond to the CH stretch for the aldehyde. And that's pretty characteristic for an aldehyde, because if you look through the table of peaks, no other peaks in common organic functional groups fall in that range. Now what if you don't have this strange cleft shape and a CCl stretch? What if you don't have the CH stretch, but perhaps you have a strong CO stretch for a CO single bond? That would be corresponding to an ester, perhaps. And what about the anhydride? Well, the anhydride has two double bond O's, so perhaps not surprisingly, you will often see two CO bands. And of course, you have the CO stretch at around 1000 to 1200 as well for the singly bound O that sits between the two carbonyls in an anhydride. Now, suppose you only have the CO double bond and you don't have any of these other features. Well, then perhaps it's simply a ketone. The ketone is a lot like the aldehyde in terms of reactivity and all that, but in terms of bonds that you can stretch and bend, it doesn't have an H right beside the carbonyl. The aldehyde has those CH stretches. The ketone does not. Now, what if we don't identify an aromatic ring? So perhaps we've ruled this out. We don't see a CO double bond. We've ruled this out. And again, we're looking at pretty simple molecules that don't have more than one functional group in them right now. Well, if we ruled those out, we still have a bunch of functional groups that are possibilities. We could have an alkane, an alkene, an alkyne, an alcohol, an amine, a nitro, a nitrile, maybe an ether, and other functional groups that might not be on this list. Well, let's say we have one of these bands to the far left-hand side, the high energy side of the spectrum, above 3100. One of these peaks, but we don't have the CO double bond. Well, if we see the U-shaped peak, very broad peak, could be an alcohol. If we see a sharper peak in that region of the spectrum, it could be a secondary amine. A secondary amine being one with only one H on the nitrogen, or a W shape if we have an NH2 group. It could be a primary amine. There are also a couple other bands that appear in that region of the spectrum. In this general region, you might also see a CH stretch. There's an H attached to an alkene, and if that's the case, of course, the alkene should also have its CC double bond at around 1650. Again, that's stronger than the CC bond in the aromatic ring, which will show you the two peaks at 1600 and 1500. Here we have 1650 for an alkene that's not part of an aromatic ring. Or you could have an alkyne. An alkyne will have a sharp peak at between 3300 and 3100, and it will also have that peak with a CC triple bond. So we could annotate this little box and say, well, it will also have the peak at 2100 to 2200 for the CC triple bond. Now, if we don't have any of those peaks there, let's say we rule those out, it could still be an ether, a nitro group, an alkane, a nitrile, an alkyne. And if we have an internal alkyne instead of a terminal alkyne, we won't have that sharp CH stretch between 3300 and 3100. That is attributable only to the CH at the end of the alkyne, the H attached to the sp hybridized carbon. You don't have an H attached to an sp hybridized carbon in an internal alkyne, but we'd still see this weak band at 2100 to 2200 for the CC triple bond. So it might be an internal alkyne. What if instead you saw a strong peak at 2200? It's still some type of triple bond, but remember, it's the polar bonds that lead to strong absorption. So that'd be a nitrile, and if you remember, a nitrile is a CN triple bond species. Now suppose we don't have that. We don't have the triple bonds at all. Maybe we see a strong peak at around 1000 to 1200, like we saw over here and here. Again, that's a CO single bond. Might be able to identify an ether in that case. The nitro group, if you haven't studied it or don't remember what it is, looks like this. And what you'll see are two peaks, one at 1350 and one at 1550 for a nitro group. Now what if you've gone through this whole thought process and you don't see any of these peaks we talked about? Maybe you only see a typical CH stretch at around 2900, 2950-ish, and maybe you just have an alkane. So sometimes in looking at a spectrum, it's not the peaks you do see, but the peaks you don't see allow you to, through process of elimination, make a selection of the correct molecule. Well, having that flowchart and talking through it is pretty abstract. It doesn't really help us to look and see what these spectra really look like. So we'll spend most of this lecture talking through spectra. This is the infrared spectrum for hexanal. If you don't know how to name aldehydes, hexanal has an aldehyde on 6-carbon chain. Now what we expect to see in an infrared spectrum of hexanal is peaks attributable to an aldehyde group. And we look for those peaks in the functional group region. We expect to see a CO double bond that will be very strong, and we know that that peak usually comes here if you look back at the table. And the aldehyde has a special CH stretch, which has peaks at around 27 and 2800. Now the 2800 peak, now in this case the 2800 peak would be overlapping whatever this large peak is that's not in that region. So although we can only see one of them, we know that there aren't any other species we talk about that has an absorption around 2700. So we can attribute that specifically to the CH stretch of the aldehyde unit. What about this very large peak here? Most organic molecules have CH units where the H's are attached to sp3 hybridized carbons. So this is simply an sp3 hybridized carbon attached to a hydrogen, and that bond is stretching. That peak doesn't give us a lot of information, it just tells us there's some sort of alkyl group attached to whatever functional group we're talking about. The next spectrum I show you is for cyclohexene. So we have a cyclic structure with an alkene, and we would expect to see again our CH stretches for a typical alkane, but we also have H's attached to the CC double bond. And that HC bond requires a little bit more energy to stretch. So that's the peak right here. That's specifically the CH stretch for that sp2 hybridized carbon attached to the hydrogen. And we expect to see a peak around 1650 or a little higher for a CC double bond stretch. And perhaps it's this one right here, but it's pretty weak in the spectrum. Now you'll often see it a little stronger in some spectra, but the CC bond is pretty low in intensity compared to the double bond for the CO stretch because of the greater polarity of CO compared to CC. It has the peak that's not very intense. How about nitrohexane? Well, this is just hexane 2,4,6, where you have a nitro group on there. And remember, the nitro group gives you peaks around 1550 and 1350 that are pretty strong. Of course, we still have some CH stretches just to the right of 3000. So we could identify this as some type of nitro-containing alkane. At this point, I should point out that although we were able to identify a nitro group here, an alkene here, and an aldehyde here, we were not able to identify for certain that we have a hexyl chain here, that we have a cyclohexyl chain here, or that we have a hexane chain attached to the nitro group here. That information cannot be gained from these spectra. But if you're facing an exam where it's like a multiple choice, where you have 4 different compounds, you should be able to identify whether you have a nitro functional group versus an aldehyde versus a ketone, etc. So let's keep looking through at some other examples of functional groups. If you see anything between 2000 and 2500, it's probably some type of triple bond. So this could be a CC triple bond or a CN triple bond. It's kind of medium intensity, which could be either one. However, here we also see a strong, sharp peak at between 3100 and 3300. This is around 3300. This is attributable to a CH stretch where that H is an sp hybridized carbon. Now you don't have that in the nitrile functional group, so we can conclude that this is an alkyne that is a terminal alkyne, and here it happens to be 1-hexyne. If you take a look at the internal alkyne, you still see the CC triple bond. It's not as intense in the internal alkyne here as it was in the terminal alkyne we saw on the previous example, but you'll see that we don't have the CH stretch attributable to an H attached to an sp hybridized carbon. So this is how we could rule out any type of terminal alkyne, and this peak is not nearly intense enough to be a polar triple bond like CN, so we could rightly conclude that this is an internal alkyne. So now we've seen this example of a terminal alkyne with a very sharp peak that's higher than 3000. What if we see this broad U-shaped peak due to a hydrogen bonding hydrogen stretching in a molecule. Well, this U-shaped peak belongs to an alcohol. So we could say this is an OH peak. These are probably just typical sp3 hybridized carbons attached to hydrogens. And we'd be able to identify some type of alcohol in this molecule. This particular spectrum is for 3-octanol. Now, contrast the broad shape of the bottom of this peak. So you see the bottom of this peak is very rounded. Contrast that with this sharp peak in that area. Now, it's not super sharp like for the terminal alkyne, very sharp. It's still broad at its base here. Right, a sharp peak will come down like this. So it's still broad, but it comes to a peak. That's typically attributable to an NH stretch. There's only one of these, not two V shapes, so it's an N attached to an H, and the other two things can't be hydrogens, they're probably carbons. In this particular case, this is a spectrum that I've sketched from a picture of diethylamine spectrum. Diethylamine looks like this. We can't tell that these are ethyl groups necessarily just from IR data. We'll learn NMR a little later in the semester. But this gives us some information on what type of functional group might be here. Now, if you have some peak that's broad at its base with two little V's, or this W-shaped peak that we talk about, then each of those two little V's is probably an NH, and the N is attached to some type of R. This happens to be a hexylamine, which has a nitrogen with two H's, and 1, 2, 3, 4, 5, 6 carbons. That would be the structure. So we've seen several examples of types of species that have peaks out here. We looked at the terminal alkyne that would have a sharp peak here. We've seen that the alkyne also has peaks in this region. And now I show you another peak in this region between 2000 and 2500 in this spectrum. So we have a very strong peak here. That suggests we have a very polar triple bond. And the only functional group we're going to talk about with a triple bond that's polar like this is the nitrile group. This particular molecule is CH3CN, called acetonitrile, and we are able to deduce the presence of the nitrile due to the very strong absorbance between 2000 and 2500. Now in this spectrum, we don't see the presence of a CO double bond. We don't see the presence of a CC double bond. We don't see the presence of a CC triple bond. We don't see the presence of any of those features to the far left, high energy side of the spectrum. This could be an alkene, or it could be some type of ether, something with only single bonds in the structure, no hydrogen bonding units. In this particular case, we do see this very strong peak between 1000 and 1200. That's the CO peak. Right? That's a polar bond, which is why it's so strong in this region. So in this case, we have an ether molecule, and this particular ether is diethyl ether. Now here we have the spectrum for a carboxylic acid. Now the carboxylic acid should have the CO double bond and the OH as part of its structure. And here we have a hexyl chain, 6 carbons in the structure, 1, 2, 3, 4, 5, 6. But we need to be able to tell when we have an OH and a C double bond O that are in a carboxylic acid, instead of an OH over here and double bond O over here. Well, what does the OH peak look like in a structure that has an OH that's not part of a carboxylic acid? Well, we've seen an example of that. So in 3-octanol, we see that we have this big peak. It's around 3500. And separate from that, we see the CH stretches at around 3000. So I want to compare that to the OH stretch area of the spectrum for the carboxylic acid. See how that OH peak for the carboxylic acid is kind of now pushing and overlapping with the CH stretch region? And here you can imagine this is the U that's kind of got the big peak sticking out of it. And you see the OH band overlaps the CH band. And that is not what we see in the alcohol like this, where the OH is not part of a carboxylic acid. That's how we could rule out an isolated alcohol like that from an OH directly attached to the same carbon as the double bond O. And of course, again, the CO double bond is very polar, comes around 1700, and it's usually very easy to see in the spectrum. So if you see both the CO double bond peak and the OH overlapping the CH region, pretty good indication you have a carboxylic acid. This spectrum has some pretty large blob-looking peaks in it, but we can go through our progressions and figure this out. We usually see our typical CH stretches around 3000. We see that here. And we see this very sharp peak here. This seems to indicate an NH bond, not an NO bond, not an OH bond, which would be a broader shape. So an NH, we have a CH, and around 1700 we have a C double bond O. This is some type of amide with an NH group, and this particular molecule, if you draw out the structure from the condensed formula, would look like this. And that differs from a spectrum like this, where we have two sharp peaks over here, this W-shaped peak, which corresponds to an NH2 unit. We also have a C double bond O over here. So this indicates some type of amide like this, with two H's on the nitrogen. This one happens to be propamide, which has this condensed formula. Now, what would an acid chloride look like? If we look back at our chart, this is one of the few examples where I said we'd have to look into the fingerprint region for additional evidence, suggesting that there's a very polar bond from carbon to chlorine, and therefore it should have a strong band. That happens to show up at 600 to 800 wave numbers. And I also mentioned the sort of cleft shape at the bottom of the CO double bond peak in that spectrum as well. So here, just to show you what that looks like in propanoyl chloride, which has this structure, we do see this sort of cleft shape in the bottom of the CO double bond peak. We see some CH stretches, which is not unusual. Most organic molecules have some CH stretches. And between 600 and 800, we're supposed to see a CCl stretch. This one's a little too high. It's out there a little bit. So maybe this is the CCl stretch in this molecule, and it lets us figure out that we have a propanoyl chloride. Now, this strange shape, again, does not appear in every spectrum for an acid chloride, so sometimes acid chlorides are somewhat difficult to pick out, especially given that you might have other peaks in the fingerprint region interfering. You may need some other techniques to help you figure out for sure what you have in such cases. And again, if we look at this spectrum, we see two pretty strong peaks, both in the area we'd expect for a CO double bond. Remember, they can come all the way up to 1850 on the chart. And if we see two of them, we might think that they're either two different functional groups in the same molecule, or if we're assuming only one functional group per molecule, pretty simple cases for our introduction, maybe it's an acid anhydride. If it is, we should also see the CO single bond stretch, which should be strong, and it should be between 1200 and 1000. We see a peak like that, so we could attribute that to a CO single bond and rightly assess this might be an anhydride. What about a molecule that doesn't have any heteroatoms? It's only got carbons and hydrogens, but it has an aromatic group. Well, I mentioned several different features we would look for in order to assess there's an aromatic group. Let's look back at that quickly. This was sort of the very first box in this decision tree I talked about. We should see CH stretches around 3,500 or a little higher. We should see two stretches at 1,600 and 1,500, attributable to the carbon-carbon bonds in the ring. And we should see small peaks that are called overtones between 1680 and 2000. Well, these are the overtones that I was talking about. You see little peaks here. Sometimes they're difficult to see, but you can see these small peaks in this region. You can also see two peaks at around 1600 and 1500. You need to see both of them, of course. So we've seen the overtones. Let's write over. We see the CC bonds in the ring. And we see some CH stretches. Sometimes people wonder why there are several of these and not just one. Well, this is ethyl benzene. So if you think about the structure of that, even if you haven't learned to name aromatic compounds yet, you have an ethyl group, so you've got some CH stretches on sp3 hybridized carbons, and the peaks on the right side, the lower energy, might be attributable to those CH stretches. But then you have some CH stretches for H's right beside the ethyl group. Those have a little bit different environment than the H's that are a little further away from the ethyl group, or the H that's as far away from the ethyl group as possible. So you have a few different CHs. They won't all come at the exact same energy. So you see a peak here, here, and here. That's why none of the peaks in the table give you one single number. Like, we don't say that a CH stretch on a benzene is exactly 3,500. We have an approximate symbol, or we have a range of values. because these are in a little bit different environments. They have slightly different bond strengths, and they'll be stretched at different energies.